Okay, good afternoon, everybody. This is question 55 from chapter 11. This is our final installment in the little mini-series on intermolecular forces. Now, in this final question, we are asked to look at several pairs of compounds. We've got 3 pairs in total. And we're going to pick the one of the two with the higher vapor pressure. And we're also asked to explain our reasoning. So let's get these things in there. All right, so we've got bromine and iodine gas. We've got H2S and H2O gases. And we have ammonia. And ammonia with phosphorus substituted for the nitrogen. Okay, let's have a look at these things. So in this case, we're talking about higher vapor pressure between the two, right? What is a higher vapor pressure? This has a lot to do with the last problem we were doing where we were comparing boiling points. So remember, for a molecule to boil, right? So if this is the liquid layer here, let's say, and we have all of these molecules of sorts, right? And they're all close together because their intermolecular forces hold them together, right? So there is whatever kind of forces between these, right? And we've seen obviously that changes on the species. Whatever there is between those things, it's going to hold them in the liquid phase. So if we're applying some amount of heat or energy or something to the bottom of this, which you see in this crude fire drawing here, we are going to boost the energy of these molecules, and they're going to start moving more and more and more and more and more, meaning that the molecules may be held like this, right? With a little more energy, they may be held like that, right? And with a little more, they may become held like this. Right? You get the idea. There's going to be more and more space between these until finally this force can't hold them anymore. When that force stops holding the molecules, and this is a necessary condition, not just a sufficient condition, the molecules are near the surface, then the molecules can't escape into the gaseous phase. And that's how we define, in a sense, the difference between the liquid and the vapor phases. All right. So when we were talking in the last question about the boiling points, we were looking at the amount of energy it took to get them from this liquid state to the gaseous state. We were looking at an energy activation difference here, where we were looking at energy on one axis, and we were looking at like the reaction process on the other one. Okay, so if we're looking at vapor pressure, we are looking to quantify the amount of the substance that is going into the gaseous phase. So you can think of that in terms of some sort of a piston cylinder type assembly, right? So this is just held in place, let's say, with some sort of like fixed amount of force, right? And because force is just displaced mass in a sense, right? Well, it doesn't need the Newton's second law, really. You know that if you're moving this and there's some weight to this and you're displacing the weight, that equals a force, right? So the displacement works in this case. So if we know what this is, as the vapor builds up, then the vapor applies pressure against the cylinder via molecular collisions, all right? And if you haven't heard all this in the class, don't sweat it. It's coming in PChem if you guys are taking it, but you are studying this with a PChem prof, so maybe it'll be helpful to you, and maybe you know all this stuff already. So anyway, the point being, the more of the species that we have in the vapor phase, the stronger the pressure will be against this, and therefore the further up or down this cylinder would be expected to travel. All right, so more pressure means this would be sitting up here somewhere, let's say, in our fictitious cylinder assembly, right? And if there's less pressure, maybe it's sitting down here instead. All right, so that's the idea. Weaker molecular forces means we get more of it into the vapor phase, means we apply a higher vapor pressure. So higher vapor pressure equals lower molecular forces, and that is the important bit here. So higher intermolecular forces equals lower vapor pressure. And that's what we're going to use here. Okay, so let's look at our first couple. Let's look at bromine gas versus iodine gas. These are two molecules. I'm not going to draw these out in this case because we're sort of familiar with how this works. These are nonpolar, right? These are going to be dispersion forces only. So when we know that we're in the realm of dispersion forces only, that means that we're looking to see which has the higher molecular mass is a way to look at it. Which has the higher amount of electrons is really what we're interested in. And in this case, it's iodine. So because the I2 compound has more electrons, that means that it's easier for the iodine to have a greater displacement of the electrons. The more electrons you have, the greater your positives will be. This goes up sort of in terms of the amount of electrons that you have available to make it happen. So that means that iodine is going to have a greater dispersion force than bromine. And that means that bromine is going to have lower intermolecular forces. Or the other way around, like where we actually have it written here, iodine has higher intermolecular forces, and therefore it's going to have a lower vapor pressure. So that's our first one. Second one, where we're looking at H2S and H2O. These both have permanent dipole structures, right? They're both going to interact with the hydrogens very strongly. Sulfur is, however, not capable of hydrogen bonding, and oxygen is. Right? You remember that the hydrogen bonding is restricted to very few species, right? Nitrogen and oxygen and such, like right along period 2 towards the right with fluorine. So that means that this is going to have a higher intermolecular force. So we're going to have a lower vapor pressure with H2O than we are with H2S gas because of the presence of hydrogen bonding. Okay, last one, ammonia and pH3, whatever, I'm not sure the name of this gas actually. Same sort of idea. NH3, nitrogen is capable of hydrogen bonding and phosphorus is not. I'm not sure why the question had both of these anyway, but the explanation is the same. So stronger intermolecular forces here means the vapor pressure is going to be lower. Right? So that means that the higher of the two, which is what we were supposed to look for, we're going to have bromine higher than iodine. Okay, let's just do it this way. Bromine higher than iodine. We are going to have H2S higher than H2O. And we are going to have pH3 higher than NH3. Hopefully that was helpful. That concludes our mini-series on intermolecular forces.